new Cube video. My name is Pavel Savianko. I'm a member of Scalasca performance analysis group in Research Center Jülich, and we are working on performance analysis on HPC software. So we develop common unified measurement infrastructure, SCORP, the tracing trace analysis tools, Scalasca tools, trace tools, and the performance profiling infrastructure framework, Cube. So in this video, it's all about the Cube. As promised, I will go today into a little bit not usual topic. I will show you or explain some internals of Cube data model. And before, of course, please subscribe so you don't miss next videos on this channel. If you find that this topic is helpful for your understanding of performance, of your performance analysis, of usage of our tools, please give us a like, and if you have any questions, write them down below in comments. So we will gather them together, and later on, maybe for sure, we will of course answer them either individually or in a separate video. Okay, but in this video I will talk about Cube data model, about internals, how to interpret data, and how it is organized, and all such details which one usually has to work out while working with the software. Okay, so Cube data model. Let's get my my notes here, and okay, here. Okay, so and Cube data model. So as the name states, that is the cube. What is cube? Cube is three-dimensional model. So we are having here some data which is organized in 3 dimensions. What are those dimensions? So in our case, these are metric. This is a call tree and system tree. So we organize our dimensions basically in these dimensions and observe a relation between them as a little bit like perpendicular. And basically the data which we collect and organize is nothing else than a mapping metric call path system tree. It goes into some value. We call it okay, here's something. We call it a severity. Okay, severity. So with other words, one gets words. One gets an answer to the questions: what happened, when, and where, basically. So, and to these 3 questions we assign a value. So value, which is our severity. Yeah. So so what are those questions? So what it is the point of our interest. So that might be a runtime of some code. It might be a number of calls. It might be number of sent bytes. It may be number of open files, open descriptors, and so on. So this is nothing else than just a metric which we are measuring, and in this way we are answering what's going on. So what is when? When is basically, so if what okay, here oops, okay, what would be time, number of calls, number of sent bytes, and so on. So that is metric. When that is basically when it happened during the execution of my code, which translates into the in these terms is it is call path. So the call path is related to the number of to the moment of execution of your code. Of course, it is not so simple like a timeline. It is so, for example, if some call is being executed multiple times, so the data will end up in the very same place, or normally. But in general, call path or call tree is related to the question when did it happen in our during our execution. So when call path in the code. Okay, so that is this what, when, and how. What would be then where question. So the typical where that's nothing else than where did it happen, number of open files or sent bytes, where in our HPC machine, in our HPC system. Yeah, so here maybe a little bit more words. So the current HPC system, this large machine, they are never monolith like a small laptop or some workstation. It's a usually huge machine consists of multiple parts. So typically they are organized as a clusters, typically, not always. And one can assign, let's say, to different parts of the machine different, let's say, labels. So let's say I paint you here schematically. So let's assume our HPC machine consists out of 3 racks. What is the typical name for it? That would be then like rack 1, rack 2, rack 3, and this rack is usually such a cabinet. It consists out of the multiple motherboards which are then located somewhere within the cabinet. Let's see, I think let's see, that would be then different, we would call them mid planes, for example, in this in this setup. So let's say it would be M1, well, it would be M1, let's say 1, because it is mid plane belongs to the rack 1. So it would be M2 1, and that would be M3 1. Okay, and the modern motherboards, they actually consist of multiple sockets where the separate CPUs are located, and it would be like maybe arranged like this, and then here, also here, and so on. So, and then, for example, this CPU would be then, I don't know, CPU, let's say on this board 6 or 3. That would be also CPU 3, and that would be CPU 3. So if we have something like such example set up, then our question where would translate or answer to this question. For example, if we have execution or the code which is running on this CPU. So what does it mean? It means that this code which we want to, or the data which we want to assign to execution on this specific CPU, one would have to assign it like to the rec1 midplane 1 and then CPU 3. If it goes, if it is about CPU 3 on rec 2, it would be then rec 2 midplane 2 1 and so on. And as we see, there is one can see hierarchical structure of such setup. So therefore, we can actually combine them into such organization like a machine. Let's say that's our machine, and that consists out of rec 1, rec 2, rec 3, and then each of them wrong color, not good. Then mid planes 1, 2, 2, 2, what would be mid plane? I don't know how many, 10, let's say 16. This is also M1, M16, midplane 1, M16, and each midplane, for example, has 64 CPUs. Then it goes into 64, CPU 1, CPU 64, and the same is in every another plane. So in such way, we have organization of our HPC system, and we can pinpoint basically execution on every single core, and with okay, the data which we are collecting is related to that core, yeah? And then we can collect all this data together, and then we have the answer to our question. So what kind of data is that, time, call, number of calls, and so on. When during the execution, that would be the call path, and where on a system, that would be the location in such we call it system tree. Okay, so this is organization of our dimensions. So, but dimensions alone is consist out of things. These coordinates, basically. Coordinates are have probably some values. So what are these values? Okay, so that would be then like we have 3 dimensions. Metric, call tree, and system tree. And what are these coordinates? So if we have a mapping metric, call tree, system tree, and it goes into some value, let's say, so that's one can the rewrites, like for example 0 0 0 goes into, I don't know, 10, 1 0 0 in 20, 5 10 100 in minus 3, I don't know, something like that. So what are these 0 0 0, what is this 1 0 0, 5 10 100, and so on. So, and here one has to take a closer look to structure of these dimensions in a cube, how in the structure these numbers basically appear, and what do they mean? Do they have some properties, and so on. So yeah, let's go into this detail. So the first, we'll take a look at the coordinates in metric dimension, and what does it mean, and how one interprets it or how one handles it. But generally, as we have seen, the trees in cube, or dimensions in cube, are organized as a trees, which means that coordinates within a dimension, they have relation to another coordinates in the very same dimension, like parent and children. It means that it's not just randomly scattered data. This data might appear randomly, but the value of, for example, for coordinate 10 is related to the value of for coordinate 1. And this relationship would be parent and child, or inclusive, exclusive, and so on and so on. So that's what we'll take a closer look. Okay, so coordinates in metric dimension. Metric dimension. Okay. So the structure of the metric dimension is the tree. Which means the relationship between different coordinates is a parent-child or parent-children. So basically the parent can have multiple children, but children have only one parent. This is this property we keep for now, but might be we can extend it in the future if it is useful. We don't know yet how, but we keep it in mind that this is just one way of organizing dimension. Maybe it will be useful to change it in the future. Yeah. So what is this metric tree? And okay. So if we take a typical example or result of measurement from Scorpy, which is coming directly from Scorpy, that would be profile.cubics. That is coming from Scorpy directly, so-called raw data. And what we see typically, if we open this file, we see their metric time. So let's do it in another color. Metric time. Yeah. We see their metric visits. We see their maximal inclusive time, something like that. The time. We have minimal inclusive time, at least in current, in latest version of Scorpy. We have also number of bytes sent, and we have number of bytes resized. And I think maybe also additional metrics about the memory, but nevertheless. So this is a list what we get, and if we maybe take a closer look in the description of metrics, they have the IDs 1, 2, 3, 4, 5, 6, and so on. And we actually in the raw, the profile data in profile cubics, we don't have any tree. I mean, this is the basic tree, or in this case forest, without any structure. It's very how this degenerated tree, let's say. Yeah. The values in the metric visits, of course, have nothing to do with the values in the metric time, because once is a number, another is a seconds or microseconds or nanoseconds. The number of bytes is number of bytes in number of units is kilobyte, megabyte, or such number. It has also nothing to do with time, so we cannot compare them, and therefore they have no relationship. So that is if we take a look at profile cubics. But if we do further operation, so-called remapping, about that I will talk in another videos. About this tool, about what does it actually make, and how one controls it, and so on. But if one performs the step which we always advise, the remapping, then one gets another file. We call it summary cubics. Yeah, so if we go here and take a look at summary, oops, that's not okay. Summary.cubix, and we open it, so we will see, we will find out hierarchy of metrics after remapping. Okay. Remapping. Okay. Yeah. One can do this remapping using either square tool coming from Scalasca trace tools, or directly the cube remap tools in as a part of CubeGUI package. Yeah, and one usually finds inside. So let's do here. One sees metric time. This metric actually split into the different submetrics, and it depends on version. I think in the latest version we split the metric into execution metric, and somewhere here, let's say, idle time. So we basically observe our whole the measurement, or the run or measurement, like starting from now till the end, and we can assign, okay, some part of code is now running, some part of code is running on some course, another course are not doing anything because nothing was spawned, but we still track this data this time, and that would be then, for example, idling time. Yeah, therefore we can assign to this part, let's say, of real time, the value, although we didn't measure it actually. Yeah, so that would be the null data, idle time, and execution. We can split in different way. So what we are doing currently is we define so-called computation metric, where we assign every user-defined code, and then we split up also different paradigms like MPI. We assign different data to OpenMP, to what is the Shmeem, for example. So these are different libraries which we can measure, and then we assign the running time, or not only time, different metrics. In this case, runtime to this spent in this within this call. So it would be then user call, MPI, OpenMP, and then of course, because the metric time got hierarchy, and in total the metric dimension got hierarchy, then we assign also IDs. That would be then, for example, 0, that would be 1, 2, 3, 4, 5, and say let's say here is 15, something like that. So, and this 0, 1, 2, 3, these are coordinates in the along the metric dimension. Yeah, and then we, if we then have some data like metric dimension, we have our coordinates 1, 2, 3, 2, 3, 4, 5, blah blah blah, 15. So these are our coordinates, and let's say we do not take a look at another dimension, so we maybe grab some data set, but this data set is along the metric dimension, and then we have let's say 10, let's say 5, 3, 1, 1, and I don't know, also 1, something like that. So then we can see, okay, the time which we assign to the metric time, the 0, is the 10 seconds. In execution we assign the 5 seconds, to the computation would be 3 seconds. In this case these are seconds, in the MPI, OpenMP, 1, 1, and so on, and then idle time 1. And of course, how the score P does, it has inclusive value, the relationship across this metric. So for example, the value time would unavoidably contain also execution inside and idling inside. Therefore, metric time actually, this is mistake, has to be 5, and here has to be, let's say, 5. So that the sum of the execution and idle should give metric time, because there is no another time than either execute or not execute. It's totally, completely distinct separation, and therefore the value of metric idle, so ID or coordinate 15, plus value in coordinate 1 should give the value in coordinate 0. And that is exactly structure and relationship between values within the dimension, within the metric tree. And the same is valid for execution. So execution I have here, like for example, that is 5. Yeah. And we see that the value of computation is 3, value of MPI 1, value of 4 is 1, and these 3 values already sum up to the 5. It means that all other values, shmem and whatever comes under it, they have unavoidably values 0. Because the relationship between execution and computation MPI is totally disjunct. One can formulate it differently. One can make allow that the value of execution, for example, is higher than the sum of all submetrics. But then, if one takes the value of execution and takes all values of all children and subtract them, there will be non-zero. So what does non-zero mean? And then one would have to say, okay, that is some part of execution of our code which is not computation, which is not MPI, which is not OpenMP. So everything what we couldn't classify and assign to some specific metric, that's some leftovers. But currently the Cube or score P formulates the metric computation exactly in this way. So it says, okay, computation is everything what happened during the execution and is not MPI, not OpenMP, not shmem, not and then a list of all the submetrics. So the computation plus others give unavoidably a metric execution, and therefore this condition leads to so-called zero exclusive time, zero exclusive value of metric execution. Simply how we define the metric computation. That's done because during the instrumentation we cannot distinguish user own code or the code which is executed in a library which we didn't instrument. So therefore definition of computation metric is such disjunct. Okay, that's about metric tree. Let's take a look what's going on in the call tree. Here is a little bit more interesting things are going on. So let's see, call tree coordinates in call tree dimension. Okay, so the score P tracks, of course, that builds up the call tree during the execution of code. So let's play some small toy example, so maybe then we understand better how it is going on. So let's build up a small scenario. Okay, let's imagine we have some code, and it has main as an entry point, of course, and it has different calls like foo, foo1, foo2, and it can call bar and bar1 and bar2, let's say like that. So let's let's see. Okay, here we have main, and we have here foo. I just write them one after another simply to separate. Doesn't mean that they really included. They can be completely scattered across the source code. They are not necessarily part of each other. They completely are arbitrary. I just call them one foo, one main foo. Let's say here is a bar, and then we have foo 1. We have maybe foo 2, and we have, let's say, bar. Oops. We have bar 1. Yeah. And let's let our program run and see how it goes. So it of course starts with main, goes like this, then it enters and maybe perhaps calls the foo. So it goes calls in a foo. In a foo, let's say it calls a bar, so it goes into bar. Then bar has executed, things have happened, it's done, so it returns back to foo. Yeah. In the foo, it also there is some execution, goes back to bar, but already with different parameters. So within a bar, maybe some condition fulfilled. So and then it executes then, let's say bar 1. Bar 1 is done as a subcall, so we go back to bar, and perhaps also then back to foo. In the foo we go also a little bit further, and then maybe in the next step we go to foo 1. Foo 1 calls foo 2, let's say, and then returns back to bar to foo. And then let's say it goes to main, and in the main it calls again, not again, but maybe directly foo 1, let's say like this. Foo 1 calls bar 1, like this, then executes, then calls foo 2, and then returns back to main, something like that. So it's a little bit arbitrary, random execution, I don't know, just invented, and see how we can what we can do with that. So let's split first this timeline into the different regions, so I can we can identify them better. So we see that main was like this, then okay, that's our timeline, and we see the different this here, tag, this, then this, tag, also, so, okay, and this. So let's maybe we do a little bit of color book. So let's color everything every time which we spent in main directly. Let's like greenish, like this. So this is obviously the part of the time which we spent in the main. Then let's see, we call the time which we spent in the foo. Let's say, let's paint it so reddish. And this, that would be that would be this, and that's all. So let's see, this time in a bar, that would be done this one, and this one, and this one. Okay, yeah. So the time in foo 1, we have here maybe not anymore so many colors. Okay, in foo 1 that would be this one, in this, and here, and here, and here. And of course then let's say, let's do that gray. In foo2, that will be done this, and this, and then in bar 1, that would be what, like this color. Okay. So we could identify every basically part of our timeline, and then we can construct out of it, of course, our call tree, which would be, we enter with main, so main, and then we see that from main we actually enter always either foo or foo1. So we have 2 children. So let's go for foo first, because it's from foo we go to bar and also to bar, and then to foo1. So we have 2 children here, but so let's see first bar. Okay, that's bar. Yeah. Okay, and then we're back to foo, that will be here, and then again bar, and in the bar we call bar 1. So the bar has a call bar 1. From bar 1 we go back to bar, and then back to foo, and then the foo we call foo1. So it's basically here foo1, and in foo1 we call foo2, that would be then another child, and then we go back to foo1, back to foo, and do I have pointer? Probably don't. Okay, we have then foo2, foo1, and from foo1 we go to foo, and then back to main. So, and then in the main again we call back to go to foo1. So we have another call here, foo1. Even that it is the same region, part of the code, but it has been called from another part of our code. So that is a relationship. That is exactly this when. Yeah, the region is the same, but it's called at different time, a different condition, different context, and therefore it has a different separate entry in the call tree. So we have foo1, and from foo1 we call bar1. The same story. It's the same region, but it's called from different place, and therefore it has different call path. And then it goes back to foo1, and then foo1 we call foo2 again. So we have here also foo2, and it goes back to main. So we have our basically call tree. Yeah, and we can actually assign different IDs, different coordinates to these entries in this call tree. The most natural probably would be so-called first entry strategy. So we assign +1 coordinate every time we see the region. For we do new entry in the call tree, like I did it just right now. So that would be, so let's do first entry. All right. Yeah, that would be first we entered the call main, so it gets the coordinate 0. Then we went into the foo, coordinate 1. Then we went into the bar, coordinate 2. From 1 we get to foo is already there. We go again to bar is okay, already there, and then we go to bar 1, it's new, so it would be 3. Then we go back to bar, it's already there. We get back to foo, it's already there, so we don't need to assign new coordinates. And then we go to foo1, it's a new call tree entry, new call path, so it would be 4. From foo1 we got to foo2, that would be then 5. From foo2 we return to foo1. Then we return to foo. This call path is still there. Main, it's there, so we don't need. And then we jump back to foo1. It's new call path, so it will be then 6. And then for bar 1, it's new call path, it will be then 7. And from it returns, and then we get to foo2. It gets the 2 to foo 2, it would be then 8. Yeah. So this is so-called first entry strategy. The another ways to assign coordinates is deep first assigning, deep first strategy, or breadth first. And this is a little bit different. So unfortunately, our call tree is actually compatible to the deep first. Therefore, it would be identical. Nevertheless, the assignment of coordinates happens not during the execution of the program, but later on when you create, for example, the cube file, or after the post-processing. And there our framework goes actually from the original call tree and traverse it in a deep first manner. So it will be then main as a first, it's again 0, then it goes foo, then goes bar 1, then goes to foo 1, 4, okay, check, that was too much, okay, 4, 4, 5, and then returns up in the 3 up to the main, then returns back to foo 1, the 6, and then 7 and 8. So it's just by accident happens that it is as identical coordinates. If the some subtree is repeating, then first entry enumeration and deep first enumeration can differ. The another way to enumerate coordinates in the call tree would be done we call it breadth first, or what's the name of this strategy? Forgot. But nevertheless, here one traverses not in the depth of the tree, but first enumerates everything in on the same level, and then it goes to the next level and goes to the next level. So in this case, it would be, let's say, bluish, right? Or green. Okay. So we go as the first is the main, so it would be then coordinate 0, and then it goes to the next level, and the next coordinates would be then here 1, but the 2 would be foo 1, so it would be then here 2. And then one goes to the next level, so it would be then 3, and one stays, one enumerates first children of the same parent. So in this case, it would be then 3 and 4, and then one goes to another parent or another element of the tree and enumerates these children. So that would be then 4, 5, 6, and then one goes deeper. That would be then 7 and 8. The different enumeration has different properties. Like for example, the deep first enumeration keeps together all children of the same parent, like literally all children up to the deepest level, and that's useful if you really need to sum up all children, all grandchildren, great-grandchildren, everything. Deep first, the breadth first way of enumeration keeps together basically children of the same level, yeah, without the children in the depth, but directly children, no grandchildren. So it is useful if you have to, if your operation consists out of summation of only one level of the first level of your children. They are kept together in enumeration. So there is a such neighborhood relationship. In the cube, the Scorpii usually creates the first entry order. So let's write it here. Deep first, and the first. So the score P creates a first entry order of enumeration, which is also very often identical to deep first. It breaks, for example, if one gets asynchronous execution, if one suddenly have to include call sub-tree within the execution that happens during the unification process, and so on. So most likely in a typical execution, if you get this profile cube X from the score P directly, and you inspect call tree, you will find out deep first enumeration. In early it was exotic case, meanwhile it's not anymore exotic case, it will be totally scrambled, but there will be then first entry enumeration. After post-processing, the enumeration is then restored to the most likely to the deep first. Internally, the cube keeps internal mapping, so the IDs which you see in a file might be either first entry or deep first, it might be, but between this enumeration and actual enumeration which cube library uses to access data, there is another layer of mapping, and this mapping creates, for example, out of this initial enumeration, working enumeration, and that might be either deep first or breadth first, because that depends whether the metric is inclusive or exclusive. How does it connect to each other, I will show a little bit later in the very same video, because it has to do with algebra, with operation which performed on data. Okay. So before going to the system tree, I remind you, please subscribe, like, and of course like, and if you have so far any questions, write them down in comments. Okay, and the last our dimension is the system dimension. Here I would probably repeat a little bit in details initial explanation. So the system tree has a little bit different properties than any another tree. It has structure, it has hierarchy, but the coordinates which we assign in this dimension, we assign coordinates only to the leaves, only to the deepest level of the system tree. Every another level is needed only to organize the data and have to show relationship between all these elements of the system tree or of the HPC system, but they do not actually get coordinate assigned. It means to this level of the system tree there is no data which is stored. We can calculate, we can deduce this data, but it's nothing is stored within a cube file. Okay, that's a little bit spoiler. Let's I explain now what does it mean actually. So coordinates for the in system tree or in system dimension. Okay, that's wrong. Dimension. Okay, dimension. So as I mentioned before, the system dimension describes our HPC system, and of course the hidden hierarchy in this dimension has a direct relation to the actual machine which is standing probably in your computation in your hall. This my writing is not the best one. The HPC system, yeah, and it maps its construction into the hierarchy of this dimension. So C system into and it's here. It's here. Okay, so what does it mean? Let's paint it as before. Maybe a little bit. Maybe we don't paint. We just copy paste where it is. And we cannot copy paste. Can we copy paste? Yeah. Let's try copy paste. Let's do this painting. Click, copy. Come here. Here. And hopla. That is our HPC system. And it consists out of the 3 racks, R1, R2, R3. It has of mid planes, M1, 1, M2, 1, and so on. And it has of CPUs. And on every CPU, for example, every CPU consists out of, I don't know, 8 cores, let's say. So the typical hierarchy, typical dimension, which we will build up then for this case, would be then, let's see if I can squeeze everything here. Oh, we will try. Okay, so our top level is the whole machine. So therefore, we write HPC, machine. It consists out of the next level would be the cabinets, because that's exactly what you have in your hall, and that's what where we create the next level. Would be then R1, R2, and R3. That would be then directly children of the element HPC machine. No. Machine. Okay, so we have the cabinets, and every cabinet consists out of these planes and motherboards. Of course, there is unit, power units, and switches, and everything else. But from computational point of view, there are motherboards. It is important to separate them because connectivity between the rack, for example, is different than connectivity between the mid planes. There is either different bandwidth or different organization of literally cabling, and therefore communication between on the level between R1 and R2 happens via different physical medium than within the plane or within the cabinet, and therefore we have to distinguish all these elements. Of course, if if you take R1, put it on top of R2 and connect them in very same way like within cabinets, then doesn't make sense to split R1 into two R2. It's simply one larger cabinet because the connectivity is the same. But as soon as the physical connection is different than between another element, so it makes sense to split it apart, because that reveals also the bottlenecks within in the message passing between rack to rack and not between the mid planes and so on. So therefore we construct such hierarchy of the system. So okay, we have R1, and then the next element would be mid planes. Let's say several. The same here, mid planes. I don't know. Let's say 16, and here would be then M plane 1 to do M16. The 16 motherboards are installed inside of the rack, and they are connected identically to each other. Yeah, but outside of the rack goes different cable, different things, maybe glass fiber and so on. Again, within the motherboard, connectivity between the sockets happens via different connection than between the different mid planes. Therefore, it has its own level in this hierarchy, and then let's see. Then our next level would be then CPU, and we have 64 CPUs, 60 within every mid plane, think CPU1, CPU64, and also here CPU1, CPU64. Of course, there are between also elements here, CPU1, 2, 3, 4, blah blah blah. I just don't write them here. The same is for other elements of our tree. It's not only for midplane 1 and 16, it's also valid for all other in between. Okay, and then every CPU has, as I mentioned, has 8 cores, and therefore we assign also the different cores within the CPU, because again, connectivity between the cores within CPU is different than between CPUs, and so on, and therefore we can write here core 0, actually 1 if we enumerate them. Let's see consistently, core 1, blah blah blah, to core 8, and that is the same for every CPU. Yeah? And in this way we have 8 cores times 64 times 16 times 3 elements. Let's calculate how much is that actually. So what that would be that? We have 8 cores. Let's say it's a very homogeneous setup. It's equal. Every rack has equal the same number of midplanes. The same midplane has a number of CPUs, and so on. So they are completely identical. One can build up, of course, such heterogeneous system where the some racks will be more powerful, more memory, but less CPU. Another racks have different kind of CPUs at such a modular setup, keyword modular HPC. Take a look at our institute. But in this case, it's very homogeneous, very identical, and therefore we can simply multiply 8 by 64, because we have 64, and then we have 16, 16, and then times 3, and in total we have 24,576 cores available for execution, and we can distinguish them one from another. Yeah? We can always see, okay, it's like 2 midplane so, core CPU so, and core so. And exactly that, these numbers from 0 to 2024, that would be then 0 coordinate, 8, 24, 5, 6, 7, 6. These are coordinates in our system tree. We enumerate only the smallest unit where execution can actually happen. So no execution happening on the CPU itself. If there is only one core, then the CPU has at least one core, so therefore there will be one core. No CPU, no execution happens on midplane itself. Yeah, so therefore we do not assign any data on this level. The data is assigned to the actual unit which performs the execution, some code. If it would be done GPU, it would be also assigned to the smallest unit where execution happens. So that would be done probably string, I think. Yeah, so, and it means in this dimension, despite that we have more elements, we have only 24,576 coordinates. They are assigned to the core, to the leaf of this dimension, and all other elements in these dimensions, they play the only organizational role. They show relationship between this data. Like for example, the data which is assigned from 0 to 8 to 7, that would be the 7th here, sorry, we know that it belongs to the same CPU. Yeah, the data which is assigned to the coordinates 16, that would be then what, 16 to 31, that would be then another CPU. Then CPU sits in another motherboard, and so on and so on. That's only this organizational aspect. Yeah, and then okay, so how out of it one gets cube basically. Okay, let's try to imagine cube with such fancy dimensions. Okay, let's do a new site. Cube. Okay, so the cube, we paint a cube. Yeah, so we have one dimension, goes here. We have another dimension, goes here, and we have, of course, this dimension, and goes somewhere there. So let's see, the dimension which goes up is our metric dimension, so that would be m. Then let's say this this metric, that would be then what, call 3 dimension, and that would be system dimension. Yeah. Okay. So, and of course, as a cube, we can split all this space into the units, into the elements, and every element will get done coordinates. So, and then every dimension we can put a tick mark. Tick, tick, tick. So in our example, we had how many we had? In the call tree we had 8, so 9 coordinates from 0 to 8. So let's put 0, 1, 2, 3, 4, 5, 4. 1. I skipped 2. 2, 3, 4, 5, 6, 7, 8. So these are our coordinates. These others are not coordinates. And in our system dimension, we actually have 24,576. We will not paint them. We will paint only first, I don't know, 10. Let's see. 0, 1, 2, 3, 4, 5, 6, 7. Obviously, this is part which belongs to the CPU 1. 8, 9, 10, 11, and go on. And that will be then another CPU. And then we have here metric 0, metric coordinate 1. Opla, what is that? 2, 3, 4, 5. Okay, so just not to clutter first. What do we have here? So first of all, in the system tree, the actually relationship between 1, 2, 3, 2, and so and other coordinates, there is no such relationship between them. So the value which is belongs to the core 0 belongs to core 0. It has nothing to do with core 25 and 11,000, because they are completely special, separate as a value. Of course, if we analyze performance, we understand that the value, for example, on core so may be different than another value on a core blah blah. Why? Because, for example, one had problem with connectivity, or some really some memory was let's say malfunctioning, and therefore access was longer, and therefore all the runtime, for example, longer. It has to do not with the relationship between the elements, but with the machine itself. Yeah, that's why there is no relationship between the elements within the system tree. But within the call tree, we have this element, we have this relationship, because we see that the foo and foo1, foo and foo1 have been called within main. Yeah, they haven't been executed anywhere outside of main. So one goes first to main, and then to foo, and then foo to something else, and then back, and so on. So everything is within. Note besides, asynchronous execution can happen asynchronously. There can be another execution which goes next to main as a task, on entry point, and so on. That would be also then like for foo1 or foo2, but then it belongs to own call path, and it has another entry point, and probably it will consist next to main and not over main. Yeah? That would be then, it would get then another own coordinates. But we are talking now about coordinates in this particular case, and they all belong to main, for example, and then bar and foo1 belongs to foo, and so on. So there is a relationship between them, and this relationship, let's paint it like, so we have coordinate 1 and 6 are related to coordinate 0. Let's see, let's have first entry enumeration, or basically red, and have it. So the coordinate 1 and 6 has a relationship to 0. So let's put it like this: coordinate this has a relation to 0. Coordinate 3 has a relationship to 2, 5 to 4, 3 to 2, and 5 to 4, and fourth coordination 2 and 4 is the child of 1, so it has a relationship to coordinate 1. So let's see this and this, and the same with 7 and 8. 7 and 8 are related to coordinate 6, like this. So we see that the data, any data which has stored under coordinate, let's say 2, it has to have, I would say, meaningful, not property, but one should, it is it's dependent on data which is stored on coordinate 1 and the 0. So they are not completely arbitrary, because of this relationship. So either the interpretation will be wrong, or one has to store this data carefully. Okay, and then along the metric, the dimension metric, we have basically layers, and 0 is the time, and if it is our profile cubics, then 1 would be visits, 2 would be number of was there, maximal inclusive time, 3 would be minimal inclusive time, 4 would be number of bytes, and in this particular case, the actual slice inside of this cube will have own unit of measurement. It would have it will be then standing for its alone, and then actually cube will transform into some lasagna or some layered structure where every layer lives on its own. So it will be then set of planes. It is not anymore a real cube. But if we are dealing with summary cubics or with a trace cubics, so basically post-processed performance analysis reports, there we have hierarchy within metric time, at least. There are more hierarchies, but that is the main. And there, of course, the metric 0 is a time, metric 1 would be probably execution. Let's see if I can write it. No, I will not write. So the execution, and metric 2 would be, let's say, computation, 3 would be, again, MPI, OpenMP, and so on, and metric somewhere 15, blah, 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 would be then idle time, and the data which is stored in every of this layer is not anymore freely independent. It has to obey this relationship like here. So the time has to consist out of data in execution plane and the idle time. So if you sum up this data, let's say sum up, then it has to result the data in coordinates 0. And the same is valid for computation, MPI, and OpenMP, and other things. So these planes are not anymore completely freely and independent. They have relationship between each other, and they are intrinsically, of course, the same, similar, like I don't know, different sorts of peers. So you can compare them. So that's why it is then cube. Yeah. Okay. So let's shortly then try to see how one actually has a cube. So if we have then this grid of coordinates, like this, I should have taken the squared paper. Anyway, so what does it mean if we have in let's say this element? Check. So this our tuplet MCS would be in this case 0. C is 1, 0, 1, 2, 3. It would be then 3, and S is 1. Right. If we interpret it, it is metric time. So what is that? It's metric time. What is the 3? 3 is bar 1. So it's execution of probably this element, this longest, this highest peak in our code tree picture. So it is bar 1. So that is time bar 1. No, not actually bar 1, but this call path to bar 1, because there is another execution of bar 1 is later on, but we are talking about the bar 1 which goes from foo 1 from main, not something else. Yeah, so that is this bar 1. That is call path, not region, and the one is core 1. Core 1 in CPU 0 and blah 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 in this hierarchy. And let's say if it is 100, so what does this mean? It means bar 1 spent 100 seconds on a core 1. If it would be let's say last coordinate 0, it will be another core, so there will be probably different. There will be not anymore 100 seconds but 101 seconds. So we know that this call pass on another core spent a little bit longer. It can happen also that some call pass wasn't executed on some core due to some if conditions or something else. Then it will be, of course, currently we assign 0, like 0 execution, although in the future we will assign hasn't been executed, so like no data. Yeah. Okay. So and then what would be then like 2, 5, let's say 10. But we have here, yeah, we have 10. 10. So we have 2. 2 was execution. 5 would be this, and 10 is here. So we going here. Check this data, and 2 is actually it's high. It's on another plane. It's not on a plane on a 0 coordinate. It's actually somewhere here. This, not that one down. Hopla, that's wrong. Yeah, probably cannot anymore. I will see if I have white color here. I don't have white color, unfortunately. Yeah, okay. So it's not this, it's this element, this here. So let's paint it. So here, this element. It's a little bit above on a plane with coordinates 2. So and that is not a time, which would be then this lowest plane, but execution, and that would be 5. And 5 is foo2. Not foo2 alone, but main foo1, foo2 call path, because there is another foo2 and another call path. So we are talking about this foo2, and then would be foo open. Foo2, and it would be then core 10th coordinate. It would be then 0 to 8, right? No, to 7s, and then 8, 9, 10. So it would be core 2 on CPU 1. We can name such cores 0 to 7, 0 to 7, 0 to 7, and distinguish. We can distinguish them only due to call path, or we can really enumerate them straight in the same manner like coordinates. So it would be then core 0, blah blah blah, 10, 8, blah blah blah, 10, 20, 15,000, and so on. In this case, let's do that. Let's enumerate them as a coordinate. So then it would be then core core 10, like that. And let's say it is 50 seconds. So this 50 seconds means that was actual execution of a full 2 on a core 10. The previous 100 seconds doesn't mean that the bar 1 has been executed really 100 seconds continuously. It can happen that it executed for 10 seconds, then idled, like stopped execution, yeah, and then again executed for another, let's say, 30 seconds, right? So this idling time is assigned to another metric, to idle time metric, and but the actual time from 0 to 100 seconds was assigned in the first case, but in the second case we actually track the execution where the CPU is working and the heat is emitted and everything. So this is 50 seconds. Another 50 seconds is idling. It's nothing. It's like switching off the core, so it's not doing anything. Can happen. So therefore we have here 50 seconds. And then if we have, for example, I don't know, let's say 100 metric ID 100, it's now arbitrary, just to be away from the region of 15. And let's say 5, also 5 and 10. So what does it mean? So okay, 100 ID, it's not in this picture. I just wanted to get away from this hierarchy of times. It might be also send bytes. Yeah, so that would be number of send bytes. Send bytes. And the same metric, the same call path, foo2, and on the core 10. And of course value might be not seconds anymore, but let's say 1024 megabytes. So 1024 times 1024 times 1024. So it has of course absolutely higher value. So it means that during this execution, during this foo2 execution, on the core 10, it's one sent, maybe at once, maybe multiple times, 1 gigabyte of data. Where we don't know yet, or probably we'll never know. In Cube we do not store where it goes. One has to take a look at the trace and to see either with Scalasca or with plugin Blade, which I introduce in another video, or with Vampire. So one can see the really connection where this data goes, maybe one or maybe multiple times. So that will be then another metric which also stored in the Cube. Of course, because it is has different data, it is not actually in a time part of Cube where the times is. It's another slice, let's say, like that. Yeah. Okay. So this is basically a relationship between the data within the Cube. Okay. Yeah. So what's one can say special also about our data model? So we have dimensions. They have relationship or structure within dimension, and coordinate. They have parent-child relation to each other. So one has to interpret data properly. And system tree has a little bit different structure than other trees. We enumerate in system tree only leaves, only lowest level of the tree. Everything else above needs only for organization, but the data is not related to each other. In a call tree, data is related between the coordinates. In a metric tree, it depends on metrics. Within the time hierarchy, of course, the data relates to each other and has interpretation. But for example, metric data on coordinate 0 is the time, and the coordinates 100 is the bytes. It has, of course, nothing to do directly with each other. Of course, it is related because during this execution we send so much data, so much bytes. there is this relationship, but the number 100 in the metric time, time, and the number million in the bytes, one cannot really compare them to each other, because one is seconds and the other is millions, and therefore one has to keep it in mind. So what's another special in our data model? The severity, so where it goes. I call it data type. Data type of severity. If you remember, just in the beginning of talk, where at the beginning of talk? Here. Yes. So we have this triplet MCS, and it is mapped to the value, to severity. So we define metric, the tuplet MCS. These are our coordinates, and where it goes to the severity. This severity might have also in a cube different type. Of course, it can be trivial, sometimes not. But one understands that, for example, different type depends on metric, what we're actually measuring. Depends. Okay. Depends on metric. Of course, metric time has a seconds, and it can be 2 seconds, 3 seconds, 5.5 seconds, 0.1 seconds. And metric number of visits cannot have half of visit. What does it mean? Maybe it means something, but not obvious. Half of visits, maybe only enter but never exit. Number of bytes, it cannot be half of bytes or 3/4 of bytes. Only if we split it really up to the bits, but current systems do not allow us to split up to the bits. So bytes is the unit, and therefore number of bytes. We do not calculate number of kilobytes. So if the metric would be number of sent kilobytes, then we would have 0.1 half or something. But we have bytes, and bytes is the minimal unit in our computer whole world. So therefore it can be only integer. So let's see, metric like time. Let's write it properly. Time, it is always we store metric time and such similar metrics as a doubles in 8 bytes format, 64 bits basically. So it has arbitrary value in this sense. The visits, number of visits, number of bytes sent, received, stored, written, we store as an integer, and also 64-bit wide currently, because the systems are 64-bit. Besides that is let's say trivial data types and most intuitive. That's one would probably expect anyhow. But Scalasca and Scorpii can do more. And for example, Scorpii can create a metric where it gathers statistic of calls, of also sent data, or of some events, how they call it, some counters. So it gathers not the data itself, but the statistic about it. So statistic is stored in so-called tau tuplet, which is then there is n, there is a sum, there is a sum of squares and mean and max. And so you can build an average, you can build a variance, you can have also minimal and maximum value. So basically you can build a small bar plot, and then you can store the statistic to every on every core, for every call path, for that such metric. And then of course you can also do algebra between it. This we'll then discuss in details, of course, later. And then it can be also exotic data types. They used very rarely, but Cube can handle them. That would be then, for example, rate. Well, we call it rate. It's nothing else than a fraction of two values, and then you can have 2/3 plus 5/7, and then you can add, you can subtract. So basically, rates like data rate or writing rate or anything. So you can create such metric and store as a data, not the numbers, but the actual rates. So we can also handle complex value, like scientific complex values. So far we actually didn't see any usage of it in computational science, but nevertheless it's possible. We can store not only complex value but a small array of n values. Currently it is n double values, so we call it n double values. It's basically like a tuplet. Complex value one might see as a pair, although it has own algebra. If you multiply one complex number by another complex number, you have to obey this algebra. By n double values, if it would be the multiplication, it would be the elemental-wise multiplication. Nothing special. It's not quote value, for example. Although one can define it, of course, but we don't do that now. We also support so-called histogram. Histogram. It is defined by minimal, maximum value, and also number of peaks or number or the resolution of this histogram, let's say. And it has also own algebra, so you can go from one histogram plus one histogram. You can create another histogram. A little bit not obvious, but one can do that, especially if it is if one has collected statistic which goes beyond this tuplet. So the bar plot, mean, max, and an average is simply not enough. Where you cannot resolve, let's say like that. Whereas the shape of distribution function is important for your analysis, then you have to go beyond tau tuplet. You have to actually do sampling of this distribution function. So you have to create such a the dataset histogram, and that is exactly what we are offering. You can create the metric where every value is a small histogram about the statistic, and then of course you can also perform the all possible operations, and you can do also the performance analysis. We go also we support so-called scaling function. Oh my god, my writing is scaling function. Yeah, so the another project, extra p, for example, can create a cube file where the as a data is not number stored, but parameters of so-called scaling function. So for example, in this case we would say that on the core 10 the whole full one, for example, that would be another metric. It would be scaling metric. Scales like constant or like linear, let's say like constant, like linear, or quadratically, or logarithmically, or n log n, or so on. So there is a set of scaling function. They are controlled by parameters, and this scaling function one can also store as a data value. One can perform algebra and display them also in CubeGUI. The only limitation between all these data types which Cube currently support, their physical representation on the storage. So basically has to have fixed size in bytes. So basically one scaling function in one for one set of coordinates, and another scaling function, another set of coordinates, and another. They all have to be described by the same number of bytes. Of course, these bytes can be zeros, but it cannot be so that one scaling function needs only one parameter, another 20. In this case, we would have 20 and 20, but first case, only one is non-zero, others are zero, for example. So this is maybe not limitation, but let's say it's anti-optimization. Let's say like that. So if you would like to stay optimal, so you would store only data which you really need. But because we have to have all severities of the same size, sometimes we store more, or we occupy more place than we actually need, and that is anti-optimization. Let's say. So that one has to keep in mind. Of course, one can think about completely another exotic data types. The only limitation is that one has to formulate algebra between all these elements. One cannot store completely arbitrary data. One has, because Cube performs algebra over it. It adds up and subtracts elements. If one can formulate what does it mean adding and what does it mean the subtraction and how does it actually work, then one can extend the cube so that one creates such a very, very exotic metric consist out of strings or write some textual data or anything like that. As long one can formulate such data types. Okay, so let's go to maybe last topics. At this moment, I would again remind you, subscribe. If you have any questions, post them in comments, and of course give us a like if you so far understand more and more of this material. Okay, and the last things which I would actually tell you is current limitation of data model. Yeah, so let's put them together. Where there are limits of such a data representation, because that actually gives you idea where development can go. So current limitation of what is that? Cube data model. So yeah, the first limitation which so far comes into mind is that that is the single cube, right? So okay, let's put accent on cube. So the first limitation is that it is a cube. So first limitation, cube, which means it has only 3 dimensions. So not x dimensions, but 3. Not. Of course, one can observe as the slice is actual unit of data model, because the slice where the time is stored is completely different than the slice where the bytes are stored. But if we take a look at, for example, metric time, we can build up the hierarchy and actually create the 3rd dimension. The same is valid for bytes. We can store total bytes and split them in sent and received, and the lost bytes and generated byte or anything like that. So we can actually create such hierarchies, and therefore it goes into 3 dimensions. So we have always only 3 dimensions: the metric, the call path, and the system tree, and no x dimensions. So let's write only 3 dimensions. So the metric, of course, dimensions. So one probably will leave it like that. The system 3 dimension, which describes our machines. will probably also stay, because we have to know what we are actually measuring, where it is it GPU literally connection to the physical part of our measurement. About call tree, that's probably the thing where one can create, let's say, new dimensions, especially if one thinks about such paradigms like tasking, where one spawns tasks and they can be executed at any moment. One actually loses. So let's go back to this timeline. So one cannot paint anymore so easily that time diagram. So one cannot show, okay, that's main, that goes food, and if it is on the level of tasking, they can be spawned at any moment, and they can be suspended, and then they can be respawned on another core. So this behavior actually disturbs call tree so much that probably in the future we will have to introduce more general description of this the description of the question when. It would be probably not anymore one dimension, or we would have to come with really fancy structure within this dimension, or it will be then more dimension. Because like for example, this the task can be spawned first in one core, at some moment can be in the middle of some another parallel execution. It executes and then it's suspended, and then it's respawned in another core. So it goes actually along the system tree, and it also overlaps with another execution. So this is might be very complex, and therefore probably this is dimension which gets extended. But currently we have only 3 dimensions, and that is why it is cube. Single cube, so multiple, or let's say cube, let's put here question mark. That is basically, do we really need a cube? Maybe we need a hypercube, or we need something else. I don't know what can be triangle. So the single cube, and then question mark. What does it mean? Cube. So currently our data model, our performance profile basically has coordinates coming from 0 to n in every direction. Yeah? Of course one can have gaps. Basically the coordinates goes 0, 1, 2, 3, and then suddenly 100, 140, and so on. But we actually speak then about so-called enveloping cube. So that would be then a cube which covers the whole range of coordinates in every direction. And therefore it means we have coordinates in the call tree, for example, 0, 1, 2, 3, 100, 120, 140, and so on. And of course we do not store all these empty gaps, but the data which would belong to coordinates, let's say what was there, 50 in this gap, would have very same properties, very same interpretation like all these other coordinates. Yeah, and therefore it is basically simply maybe missing, but part of very same data set, and that's why it is still single cube. But it doesn't need to be like that. It can be, of course, multiple cubes. It would have their own coordinates and their own set of interpretation of dimensions, and they can be also kept together as a performance descriptions. So currently we have only one single cube, but one can go also in direction to have actually multiple single cubes. It can be also done for the optimization exactly to avoid these gaps. Like for example, if we have a gap in the into the system tree and in coordinates, and a gap in the call tree gaps, of course we either we store like enveloping, or we store actually 4 resulting small cubes where the actual data stored. So we kind of end up then with 4 cubes instead of 1. They are the same in their nature, they are the same coordinates, or the coordinates belong to the same measurement and so on, but we have done small cubes. That is the technical aspect of such things. Okay, yeah, then we have also, so that is one limitation, 2. Well, I would call it no hidden dimensions. So what I actually mean. So the currently we have to any data value to every value of coordinates only 3-plet, let's say. But one can imagine like that, for example, for the data for the call path from 0 to 100, let's say, we have only 3 coordinates: metric, call tree, and system tree. But for the part of the call path from starting from for the part of call tree starting from call path 100, let's say, to 200, we did some very fancy measurement, which we don't do now, but we could. And actually we store there not cube with 3 dimensions, but for example with 4 dimensions, hypercube, or anything else. So we would have basically the structure of dimension depending on the value of call path, of the coordinates in call tree. So we kind of get such enveloped maybe additional dimensions, and they are existing only in the part of our data. So these things we don't have now, but we could. So this is it means if we work on this data model, we would have to have the 3-plet everywhere independently on the value of coordinates or our data values. Yeah, that's what I call with no hidden dimension. One can make such hidden, but one doesn't have it. Then, and the last probably maybe limitation, which is now in my mind, is that we have all the same data type within slice, within the metric. So all times are stored as a double, and that's everywhere. One can probably think about such situation that we will actually change data type which we store depending on our need, let's say like that. So for example, if we know that precision and range of our data requires only 3 bytes and not 8 for description, then we don't need to store the 8 bytes. We can store with using 8 bytes only these parts of call tree or of system tree where the precision allows, and in parts of measurement where precision is required, we could widen the data type. Yeah, that would lead that to the very heterogeneous cube. We would still have one cube, we would have all the same thing, but the data precision is, let's say, low, maybe on top, on the metric, on the call path main, and so on, but it increases at this really fine grade to the very deep, very small calls. Or one would reinterpret this 3 bytes. Some are seconds, and if we go down, the same 3 bytes, but it would be nanoseconds. These are, that's what I call same data type. Same data type within metric. Same, so I will put a question mark because that is exactly what we question it, and then we remove this constraint with this restriction, and then we allow different data types. So technically it means like 1 byte, 5 bytes, 8 bytes, and so on. No hidden dimension. this question. Okay, so these are our current limitation, which pops up in my mind. Of course, one can think about maybe something else. I don't know, but this is already enough. So if one encounters the problem that the performance cannot be described within our current data model, like really intrinsically, then this is already aspects which one can take as a starting point and think, okay, so if we go into hypermodel, into multiple cubes, maybe some very fancy hidden dimensions, do we solve? Can we then represent our performance or not? Maybe then we can reinterpret our measurement data within very same data model. So these are all different things which one can work on. Okay, so that would be so far it's about the CubeGUI data model in this lecture. I showed you how the dimensions are constructed and which relationship different coordinates within this dimension have to each other, how the system tree is actually special, and how one interprets the relationship between different values within this cube data model. I started to talk about such words like inclusive, exclusive value, different data types, and so on. But that is exactly the topic for the next lecture, where I would explain you this. What does it mean inclusive and exclusive metric, and what does it mean for algebra and maybe interpretation of such metric. This would be the topic of the next such lecture. On this lecture I am done. Please subscribe if you find this topic is useful for you, for understanding. Give us a like. If you have any questions, post them into the comments, and see you next time.